Okay, so imagine this. You're building with like the tiniest Legos ever.
Yeah.
And you're trying to make something that won't just fall apart the second you let go.
Yeah.
Turns out the universe is kind of doing the same thing. And physicists just figured out a new rule.
Wow.
We're diving into this whole world of plutonium.
Oh, okay.
Specifically a brand new isotope, Plutonium-227.
Okay.
Now, if that sounds a little intimidating,
Yeah.
don't worry, because by the end of this, you're going to be
Right.
sounding like a total pro at your next trivia night.
I love it.
But for real, though, this discovery, it's not just like adding another, element to the periodic table. This is like rewriting what we thought we knew about how atoms even hold themselves together.
Yeah, it's really capturing everyone's attention because it's challenging those assumptions.
Totally.
Yeah.
And can we talk about the pressure on these researchers over at the Chinese Academy of Sciences for a sec?
Yeah.
They created this isotope plutonium-227 for the very first time. And this wasn't some, lucky accident either.
Yeah.
They used this crazy precise method called fusion evaporation
Right.
at their heavy ion research facility.
Oh, wow.
So
It's incredibly complex.
Oh.
They're basically smashing atoms together at incredibly high speeds and then observing what happens.
oh, wow.
And in this case, they observed 9 decay chains to be sure that they actually created plutonium-227.
9 decay chains.
9?
My brain can't even fathom that level of detail.
Yeah.
But okay, before we even get any further, I think we should make sure we're all on the same page.
Oh.
Can you give us a quick explanation of what an isotope even is?
Sure.
Because I think some of us might have slept through that part in high school chemistry.
Of course. So you probably remember that atoms are made up of these 3 tiny particles.
Wow.
Protons, neutrons, and electrons.
Right.
And it's the number of protons that actually determines what the element is.
Okay.
So any atom with, let's say, 92 protons will always be uranium.
Okay, got it.
Isotopes are like variations of the same element. Okay.
They still have that same number of protons, so they're the same element, but they have different numbers of neutrons.
So it's kind of like, how you were saying before is like different versions of the same Lego brick.
Yes, it's
Same like basic shape, but maybe some of them have like extra connection points or something like that.
Yes, that's a great way to think about it.
Okay.
And just like some Lego structures are more stable than others, some isotopes are more stable than others, and this is where those magic numbers come in.
Magic numbers. Okay, now you've definitely got my attention. This is starting to sound like something straight out of Harry Potter.
Well, it's magical in a scientific way. In nuclear physics, magic numbers refer to those specific numbers of protons or neutrons that create this really stable configuration within an atom's nucleus.
Okay.
Think of it like this.
Yeah.
When an atom has a magic number of protons or neutrons, it's like everything's in perfect balance and it makes it really resistant to decay.
So these magic numbers, they basically hold the key to how stable an atom is. Exactly. It's the combination of those protons and neutrons dictated by these magic numbers that determine how stable the element is.
Okay. Okay, so I think I'm starting to get this whole magic number thing. It's like the VIP list for making sure an atom is stable.
Right.
Right.
Yeah.
But so where does plutonium-227 fit into all of this?
Well, that's where things get even more interesting.
Okay.
Plutonium-227 sits really close to a magic number, specifically 126 neutrons.
Okay.
But it's also what we call a Transuranium element, which
Yeah.
basically just means it's heavier than uranium.
Okay.
And those elements, they kind of play by a different set of rules.
Oh, really? What do you mean? So it's like the Wild West of the periodic table out there.
Yeah, you could definitely say that.
Okay.
They just aren't as stable, and they tend to decay a whole lot faster.
Oh, wow.
It's like you're trying to build this huge Lego tower.
Yeah.
The bigger it gets, the more likely it is to just completely fall apart.
Right.
It's just a matter of time.
Okay, so is plutonium-227 like this daredevil then? Like pushing the limits of how big and unstable an element can get and still hold itself together.
Exactly. And by studying isotopes like plutonium-227, it helps us understand if these rules of nuclear stability even still apply when you get to these super heavy elements.
Oh, wow.
Or if they completely break down.
So are you saying that these magic numbers might not be as straightforward as we thought?
Maybe.
Like maybe the VIP list gets a little shorter the heavier the element is?
That's a million-dollar question. This discovery is making us rethink how much influence those magic numbers have as we move towards heavier and heavier elements.
Oh.
It's like we're getting this sneak peek behind the curtain of how the universe works.
So it's like we thought those magic numbers were the answer, and now we're finding out there's a whole other chapter to this story.
Right.
But, okay, this is all super fascinating. But I think I speak for a lot of people when I say, why does this matter?
Okay.
What are the implications of this for people who don't spend their days thinking about nuclear physics?
That's the beauty of fundamental research. Plutonium-227 itself might not have like these everyday applications,
Yeah.
but what we learn from it could lead to some really big advancements down the road.
Okay, you have to give me a sneak peek. What kind of advancements are we talking about here?
Oh, one of the biggest ones is how we deal with nuclear waste.
Okay.
Right now, it's a huge problem because it stays dangerously radioactive for a really long time.
Yeah, I've heard about those underground storage sites,
Right?
and they have to be guarded for like generations.
Yeah.
So something out of a movie.
Exactly. And imagine if we could take what we're learning from these super heavy elements
Yeah.
and use that knowledge to figure out ways to neutralize that waste quickly and effectively.
That'd be huge.
Right.
Not just for us, but like future generations too.
Exactly.
So safer nuclear waste management, that'd be a huge win for everybody, right? But what else is there? What else are scientists excited about when it comes to this new research?
Oh, there are a lot of other possibilities. This kind of discovery, it can have ripple effects like across tons of different fields.
Okay, like what?
Well, for one, think about nuclear medicine.
Okay, yeah, that's something that's relevant to like everyone.
Exactly.
So tell me more.
So imagine being able to like target cancer cells, but with way more precision, deliver the treatment exactly where it needs to go, and minimize those awful side effects.
Wow.
Or picture totally new imaging techniques that give us a view inside the human body that we've never had before.
Wow.
These are just some of the things that this research could uncover.
So we're talking about potentially revolutionizing healthcare.
Right.
Just from understanding how these tiny atoms work.
It really is remarkable, and it highlights why this kind of fundamental research is so important.
Right.
You know, sometimes we explore the universe at the tiniest level,
Right.
and it leads to these huge breakthroughs that impact our everyday lives.
It's like that saying, right? The universe is under no obligation to make sense to us. But there we are trying to piece it together one atom at a time.
Exactly. And sometimes those tiny pieces, they end up changing the world, and that's why it's so important to support this kind of research.
Totally. So to wrap things up today, we traveled to the edge of the periodic table. We explored this wild world of isotopes and how one newly discovered plutonium isotope is making us rethink what we know about nuclear physics.
And how those discoveries have the potential to lead to some pretty incredible things.
Yeah, like safer ways to deal with nuclear waste or even completely new medical treatments. And on that note, we'll leave you with this. If we can create new elements in a lab, what does that say about what humans are capable of?
And what other wonders are out there just waiting to be discovered?
Until next time, keep asking those questions and stay curious.